In a previous video, we saw examples where the ratio test was inconclusive, but nevertheless, the root test was able to determine convergence of the sequence. And I mentioned that was a general case, that the root test was usually a little better. In some occasions, it would be able to tell convergence in cases where the ratio test would not be able to do it. So let's tackle that right now. That comes from this theorem that I wrote here. I wrote it for sequences of positive numbers because in the end, when we are looking at the series, right? Then we are going to write the ratio or the root of the general terms. And here we write them with the absolute values. So in the end, instead of writing the AN, I decided, okay, let's write CN for the absolute value of the AN. So that's the reason why it's written for sequences. Okay, but here we are saying the same quantities that were involved before, that the lim-inf of the ratio is always less or equal than the lim-inf of the root, and the lim-sup of the root is always less or equal than the lim-sup of the ratio. Okay, what's the big deal about this? From 2, we see that the ratio test, if the ratio test shows convergence, okay, that means that the lim-sup here is less than 1. Okay, that would mean automatically that the root test is also going to show convergence. Okay, so again, if the ratio test shows convergence, then so does the root test. So this means whenever the ratio test works, the root test also works. But there may be cases where the root test works, okay, and the ratio test doesn't. We saw examples of this in the previous video, okay, where this was exactly equal to 1, but then the lim-sup of the root was precisely less than 1. Okay, so that's the important thing here, that there will be cases where the root test shows convergence and the ratio test doesn't. Okay. Now, whenever the root test is inconclusive, okay, looking at 1 and 2, that I'm going to copy paste. What do we have? So we have that the lim-sup is going to be equal to 1. And actually, we don't need the first equation, so let's cross it out. And then if we read here, what do we see? We see that the lim-sup of the ratio is bigger or equal than 1. So that means that the ratio test is inconclusive too. Okay, so overall what we are saying is when the ratio test is inconclusive, the root test may still be able to say something, but if the ratio test is inconclusive, sorry, the root test is inconclusive, then that's it. There is nothing the ratio test can add to that. Okay, so in conclusion, the root test is a bit more powerful. All right, so let's prove the theorem. The proof of 1 is in the exercises. for this week. Okay, so we will prove 2. As before, we are going to define alpha, which is the lim sup of Cn plus 1 over Cn. And we are going to assume that alpha is finite, because otherwise it's silly, okay? If we are saying that the lim sup is infinity, then of course the lim sup of the square root of the root of the Cn is finite, okay? Well, is lesser or equal than infinite. Otherwise, let's write this properly. Otherwise, to reach lim sup of the square root of n Cn lesser or equal than infinity, which is obviously true. Okay. All right. So by definition of lim sup, this is the same trick as before. We saw this in a previous video. We can just fix any beta that is bigger than alpha, and know that there exists some n such that Cn plus 1 over Cn is lesser or equal than beta for all n bigger or equal than capital N. Okay, from there we get Cn plus 1 lesser or equal than beta Cn, and here remember this is for every n bigger or equal than n. We do just as in the proof of the ratio test. Okay, we just take Cn plus 1 lesser or equal than beta Cn, Cn plus 2 lesser or equal than beta Cn plus 1 lesser or equal than beta square Cn, and so on. Okay, in general, Cn plus p lesser or equal than beta to the power p Cn. And here we can rewrite n plus p as lowercase n, and what we have is Cn lesser or equal than beta to the lowercase n minus capital N Cn. Okay. And from here we are set, because we can just write the nth root of Cn lesser or equal than so Cn divided by beta n nth root times beta to the n, take the nth root, leaves beta. This part, as n tends to infinity, becomes 1. So what we get here is that the lim sup as n tends to infinity of the root is lesser or equal than beta. Okay, but beta was arbitrary, could be any, as long as it was bigger than alpha. So we can just let beta tends to alpha, and we get what we wanted, that the lim sup of the root is lesser or equal than alpha, which is the lim sup of the ratio. And we are done here.